Greetings to everyone. I am Hithendra, working under the guidance of Professor Raghu V. Prakash from Indian Institute of Technology, Madras, India. The title of this presentation is Impact of Cracks and Interference on the Lozenge Pattern of Joints. This slide gives the agenda for the presentation. Several types of joints are used in industries such as rivets, bolts and nuts, screws, pins, and welds. All these joints are widely used in almost all areas of engineering such as aircrafts, automobiles, ships, boilers, bridges, and others. During their lifetime, several components undergo dynamic loads resulting in formation of cracks at the joints and further their propagation. There are several factors which affect the life of these joints. For example, life of riveted joints depends on parameters like riveting sequence, pitch and diameter of rivets, squeezing force, interference, material, and friction. Many studies are available related to these parameters in literature. However, most of the works dealt with total fatigue life, and almost all of these studies were conducted on lap and butt joints. Limited studies were conducted in the presence of an initial crack and variation of SIF during its propagation. Joints arranged in special patterns such as lozenges are yet to be explored fully. The objective of the present work is to fill this gap to some extent by conducting studies on lozenge pattern of joints. This is a double strap butt joint of plates with rivets in lozenge pattern. Current focus is on the straps here, as they are the weaker elements when strap thickness is less than or equal to the plate thickness. Considering 100% load transfer, the strap under consideration in this study can be assumed to be held in position by left half of the rivets and loaded by the right half of the rivets. Considering this symmetry, this can be further simplified as an edge-loaded plate fixed at 6 joints in 3-2-1 pattern. For this configuration of strap plate and joints, as part of this work, 3 studies were conducted. First one was a study of crack emanating from rivet joint at one end of the strap plate and propagating up to the joint at the other extreme end. At each joint L1 to L6, variation of loads during crack propagation and the change in the stress intensity factor at both the crack tips were estimated. Simulations were run at various interference levels and best level at which SAFs are minimum was identified. Variation in the joint loads due to the change in the interference levels was also assessed. The second study deals with the crack emanating from the joint at the center and propagating towards the joints at the two extremes symmetrically. Variation in the SIF at different interference levels were recorded. Based on the stresses developed in the plate at the joint, attempts were made to identify the loss of interference during crack propagation. The third study deals with variation in the SIFs and redistribution of stresses at the centrally located crack in presence of additional cracks at the joints on either side of it. Multiple combinations of crack sizes at different interference levels were studied to identify the case yielding the highest SIF and to identify the most beneficial interference. Henceforth, the term pin is used interchangeably with rivet, given the applicability of the results to pin joints as well. Moving on to the geometry used in this work, a finite width plate of dimensions 60 mm by 60 mm with 3 mm thickness was considered with the 6 holes of 5 mm diameter and rivets arranged in lozenge pattern. Both the pitch and back pitch of the rivets are 3D with joints L1 to L3 in row 1, L4 to L5 in row 2 and L6 in row 3. Size of pin vary corresponding to the interference levels of 0.1%, 0.15%, 0.2% and 0.3%. Coming to the geometry of cracks used in the study 1, the simulation started with the absence of crack, then starting with the initial crack of 7 mm, it is extended up to the maximum crack of 37 mm. Beyond this, the plate would not be able to hold the applied load. The definition of crack length encompasses the diameter of holes as well, and the crack length 2A denotes D plus 2L, where L is the crack length from the surface of the hole. For the study 2, these are the crack lengths. For the study 3, an initial crack is assumed at location L2 and additional cracks were introduced at locations L1 and L3. This table shows various combinations of crack lengths used. In all these studies, cracks were considered only at the first row, since it was observed during one of our previous works that the damaging effects of cracks in rows 2 and 3 are insignificant compared to the ones in row 1. Plate and pins are made of mild steel with elastic modulus of 200 GPa, Poisson's ratio of 0.3, tensile yield strength of 250 MPa and ultimate strength of 450 MPa. Remote stress of 80 MPa was induced in the plate by applying a load of 14,400 newtons at one plate with the fixed pin locations. To assess the influence of interference, all studies were initially conducted at zero interference and then at interference levels of 0.1%, 0.15%, 0.2%, and 0.3%. 2D linear elastic models under plane stress conditions were used for estimating the stress intensity factors in mode 1. SAF computations were performed using FE software ANSYS. At the contacts between plate and pin surfaces, friction coefficient of 0.2 was considered. The figure here shows a typical mesh generated for one of the test cases. The mesh parameters used to run the test cases were verified by comparing the theoretical and FE results for a standard cracked plate available in literature. The percentage error between theoretical and FE results was negligible, that is less than 3%. Let us start with the results of study 1, where crack propagates from one end to the other. Crack is not symmetric with respect to the geometry of the plate, and SAF at two tips 1 and 2 vary. This variation is plotted in the graph here. The two discontinuities in the SAF plot for tip 1 is due to the presence of rivet holes at locations L2 and L1. At the initial crack size of 7 mm, SAFs at both the crack tips are very close with around 5% difference. As the crack starts moving towards joint L2, difference between tip 2 and tip 1 increases. As the crack starts approaching the joint L2, SAFs at both crack tips reach identical value, and just before they reaching the joint, SAF at crack tip 1 surpasses the SAF at crack tip 2. After joint L2 is crossed, SAFs repeat the same pattern at L1 also. It was also observed that when the crack is resumed after crossing the joints, SAFs at tip 1 are a little less than the values obtained just before reaching the joint. At joint L2 it was 1.85% lower, and at joint L1 it was 3.34% lower. Variation of SAFs at different interference levels are shown here. With the increase in interference, the difference of SAFs at crack tips 1 and 2 reduces, except when the crack is nearest to the joint location, where SAF at crack tip 1 dominates the value at crack tip 2. These figures show the variation of SAF at crack tip 1 at different interference levels and the percentage change with respect to 0% interference. In contrast to the results from available literature on interference at joints, where interference up to certain levels produced a reduction in SAF at all crack lengths, in this study it is observed that most of the beneficial interference for joints varied with the length of the crack. These plots are for crack tip 2 at different interference levels. Considering both crack tips, the best uniform interference that could be provided is 0.15%. With the progress of crack from L3 to L1, horizontal and vertical reactions on these pins also vary. This plot shows the variation of horizontal reactions. Being in the first row, pins at L1, L2 and L3 carry most of the load. Maximum variation of load is observed on the pin at joint L2 with a drop of around 80% compared to the case of absence of crack. This plot shows the variation of vertical reaction on the pins. The variation of Rx at all joints are plotted for different interference levels of 0.1%, 0.15%, 0.2% and 0.3%. It can be seen that as the level of interference increases, with increase in crack length, the difference in loads carried by pins L1 to L3 reduces. Here, the same results are plotted with respect to each joint locations at different interference levels. Similarly, the variation of vertical reactions Ry at joints are shown here. Now, let us move on to the results of study 2, that is crack propagation from joint at the center of the plate to the joints at the end of the plate. This figure shows the variation of SAF values during crack propagation at different interference levels. For crack lengths up to 11 mm, interference of 0.1% is the most beneficial one, with around 20% reduction at 7 mm crack length. The reduction for beyond 11 mm, reduction in SAFs is in the range of 5 to 10% for all interference levels, except in the case of 0.3%. Apart from SAF, to capture the effects of loss in interference between the plate and pins at joint L2 during crack propagation, several parameters such as normal stress, hoop stress, contact pressure were assessed. Among them, normal stress in the direction of application of load was found to be the most suitable one. The figure here shows the values of normal stress in the direction of application of load for all crack lengths and at all interference levels. With increase in interference, the normal stress at a joint also increases. In the plot, when a straight line is drawn from a given higher crack length and interference towards the lower crack length, the straight line intersects the curve of lower interference at a lower crack length. For illustration, if a line is drawn from the normal stress value of a cracked joint with interference of 0.15% and crack length of 15 mm, it intersects the 0.1% interference curve at a crack length of 7 mm. This implies that the normal stress at the hole is same in both the cases. This is another illustration. Not just the normal stress but also the measured von Mises stress at the hole and the loads encountered by the pins at the joint are found to be equal. So it can be inferred that for a joint with relatively longer crack at higher interference, there exists a cracked joint with a shorter crack and lower interference where the stresses and load reactions are equal. Now let us move on to the results of study 3, that is redistribution of stresses and variation of SIF at L2 due to the presence of additional cracks at L1 and L3. Stresses are measured on the half circumference of the hole at L2. This plot shows the variation of SIFs at different combinations of L1, L2 and L3 at 0% interference levels between plate and pins. For any given crack length at location L2, presence of cracks at L1 and L3 yielded higher SIFs. Also, higher the size of neighboring crack, greater is the increase in SIF at L2. These are the results of SIF variation at L2 cracks with respect to various interference levels. It can be observed that as the level of interference increases, the difference in SIFs at all crack lengths reduces. Similarly, the variation of SIFs with respect to different crack sizes at L2 at all interference levels is shown in these figures along with the corresponding percentage change in the SIFs with respect to 0% interference. As the crack size at location L2 increased, the percentage difference in SIF between the cases of with additional crack and without additional cracks at L1 and L3 reduced. Except a minor exception, 0.15% interference yielded the best reduction in SIF, varying from 5% to 14% depending on the length of the crack at L2. These figures show the typical variation of normal stress and hoop stress on the half circumference of hole at L2. There is rise in stress level at L2 in presence of neighboring cracks, and higher the length of neighboring crack, greater is the increase in the stress level. Either of the two, maximum normal stress or maximum hoop stress, can be taken as parameter for quantifying the variation of stress distribution due to the presence of neighboring cracks. Here, maximum normal stress is taken as a parameter. These plots show the percentage difference of maximum normal stress at L2 in the presence and absence of cracks at L1 and L3 at different interference levels and different crack lengths at L2. It can be seen that the plots are almost similar, which implies that the maximum normal stress at L2 is governed more by the size of neighboring cracks rather than the size of crack at L2 itself. With the increase in length of neighboring crack, in all cases there is an increase in normal stress in the plate at L2. The highest percentage increase is close to 37% in case of 0% interference level and neighboring crack size of 11 mm. Studies were conducted on Lozenge pattern of joints with cracks propagating from joint at one extreme end of the plate to the other end. Variation of loads at each joint and change in stress intensity factors during crack propagation were estimated. Studies were also conducted on cracks emanating from the joint at the center of the plate and propagating symmetrically towards the joints at the two extremes of the plate. Crack lengths and interference levels were identified where a lengthier crack at higher interference produces the same reactions and stresses at the joint as the ones generated by a shorter crack at lower interference level. Influence of additional cracks on the stress redistribution and stress intensity at an existing crack were also studied. In each of the above cases, influence of interference on stress and stress intensity factors was quantified and the most beneficial level of interference was identified. These are some of the references. Thank you.